In this video, we continue with complex variables. So we discuss, in a previous video, we have discussed the preliminaries, some basic concepts about complex variables and a complex function of a complex variable. In this video, I will give a quick introduction to analytic functions. So I hope to cover point numbers 3, 4, 5, 6, perhaps 7 and 8 also. So let's begin. Before I give the definition of an analytic function, I wish to review some theorems of real calculus. So if f is a function from a domain D to R, so R is the set of real numbers and D is a subset of R. And suppose G is another such function, then we know that the addition of let us also assume that these two functions are differentiable. So we are looking at two differentiable functions. Then there are theorems which conclude that the sum is a differentiable function, the difference is a differentiable function, a scalar times f will be a differentiable function, the product of these two will be a differentiable function, the quotient whenever defined will be a differentiable function, the composition shall be differentiable. So these will be all differentiable functions. All these theorems carry over to a complex function of a complex variable. R is a subset of C. All right. So in other words, I'm taking a shortcut. I'm just saying that the theorems that you have seen in the context of real variable calculus, they are valid here also. Other theorems like, if a function is differentiable, it is automatically continuous. Such theorems are also valid in the complex case. Now let's come to the definition of an analytic function. So when do we say that a function is analytic? So let f be defined on a region R. Okay, so if you wish to draw the domain, let's say that this is our R, this is the domain, and we want to understand what is the meaning of saying that f is analytic at A. All right. So the short definition is that if f is differentiable at all points in a neighborhood of A, then you say that f is differentiable at f is analytic at A. So this can be made a little simpler, and rather than looking at any neighborhood, we could just say that so let us take a ball around this point A. Suppose the radius is R and Z is any point in this ball. So Z belongs to B, R, A. So if there is a ball such that f dash z exists for all z in this ball, then you say that f is analytic at A. If f dash exists for all z in this ball, okay, then f is analytic at E. And if f is analytic at A for all A in R, then in that case we say that f is analytic in R. If f is analytic at each A in R, then f is said to be analytic in R. All right. If f is analytic in R, then okay. So first, let me not discuss analyticity in R. Analyticity at a point. A consequence of analyticity at A is the Cauchy-Riemann equations. So I wish to discuss the Cauchy-Riemann equations now. If f is analytic at A in R, then f satisfies the Cauchy-Riemann equations. What are these equations? So we'll discuss the Cauchy-Riemann equations now. Okay, let f be equal to u plus iv, where u is a function of x and y and v is a function of x and y. So what is one doing here? One is writing, so our convention is z is x plus iy. Okay, so you can think of z as the point x comma y. Okay, yeah, there's no harm in writing it like this. And what one is saying is that u is the real part of and v is the imaginary part of f. Okay, so under the assumption that f is analytic, then this implies dabba u by dabba x is same as dabba v by dabba y, and minus dabba u by dabba y is same as dabba v by dabba x. So these two equations are called as the Cauchy-Riemann equations. Another consequence of analyticity is that the first order partial derivatives, in fact, partial derivatives of all orders of u and v are continuous. They exist and they are continuous. All right. Partial derivatives of all orders of u and v exist and are continuous. All right. I wish to use a shorter notation for da by u by da by x. So the same equation can be written as u sub x. So this stands for da by u by da by x. So the Cauchy-Riemann equations can be written as u sub x equal to v sub y and minus u sub y equal to v sub x. It will be rather easier to write these equations like this. Okay. These conditions are not sufficient. So, you know, that if f is u plus iv and star holds does not always mean that f is analytic. Okay, what is needed is that if the first order partial derivatives are also continuous, then the function becomes analytic. Okay, so what is needed is okay, so let's put it as a theorem. If star holds and the first order partial derivatives are continuous, then f is analytic. Okay. I shall now quickly define harmonic functions. So let f be a function from D to R, where D is a subset of R cross R. So f is a real valued function of two real variables. Okay. If fxx plus fyy equal to 0 and the second order partials the second order partial derivatives are continuous, then f is said to be harmonic, said to be a harmonic function. So if f satisfies a partial differential equation like this is called as the Laplace equation. So a solution of the Laplace equation which has continuous partial derivatives, the order 2 partial derivatives are continuous, such a function, such a solution will be called as a harmonic function. Why are we discussing harmonic functions here? They have got a nice connection with analytic functions. What is that connection? So if f, which is equal to u plus iv, if this is analytic, then u and v are harmonic. In other words, if you are seeking solutions of the Laplace equation, then you get lots of solutions from analytic functions. So pick up an analytic function, its real part and imaginary part is going to be a solution of that. Right now we are not looking at boundary conditions and other things. All right. Okay. And if you have a situation like this, then u and v are said to be harmonic conjugates of each other. Okay. So u and v are called harmonic conjugates of one another. Okay, so I think this is all in this video. In the next video, I will take a few examples, some illustrations, which will employ the Cauchy-Riemann equations, and I will prove to you that if u and v are the real and imaginary parts of an analytic function, then they are harmonic. So that's all in this video.